In example 17, we want to look at an amortization problem, which is the idea of paying off a debt in equal installments, usually monthly. So if a debt of $A with an interest rate of I is equal to R over K per period, where R is the interest rate on the loan and K is the number of compounding periods per year, is amortized by n equal periodic payments made at the end of each period, then the size of each payment is going to be equal to A times I over 1 minus 1 plus I raised to the negative n power. There's a lot going on here, but we'll walk through this in an example, see how we put all this together. But something to keep in mind is that in this context, I is not the imaginary number. It's not equal to the square root of -1. I is being used as a placeholder for this expression R over K, where again what we're doing is taking the interest rate divided by the number of compounding periods per year. We're going to look at this in the context of a family purchasing a home for $275,000. They have $63,250 for a down payment. Assuming they can get a 15-year mortgage at 7.6% interest per year on the unpaid balance, we want to use Wolfram Alpha to find the following. So first, how much will they have to pay per month, assuming the payments are amortized? If we're talking about paying per month, that means that value for K above is going to be 12. There are 12 compounding periods or 12 pay periods. The value for A is going to be the value of the house, $275,000 minus the down payment of $63,250, meaning the loan amount will be for $211,750. Our value for N will be 15 years times the number of compounding periods per year. So we're going to make 12 payments a year for 15 years, since that's the length of the mortgage. That's going to equal 180. And our value for I will be the interest rate, 0.076, divided by the number of compounding periods per year, which is 12. To enter all this into Wolfram Alpha, we'll need to be quite careful with our use of parentheses, but we'll start off with our value A, which is the total amount of the loan. We'll open up a set of parentheses, and then inside another set of parentheses, we'll enter 0.076 divided by 12. That's our value for I, which we want to input as that exact amount. If instead we put in a decimal approximation for that result, our answer would end up being a little bit off. So that's the expression I in the numerator. And now we'll divide this by this complex expression we have in the denominator, which is 1 minus, open up another set of parentheses, 1 plus 0.076 divided by 12, raised to the negative 180 power. And then we'll close off an extra set of parentheses to keep that entire denominator together. Sorry, I paused in the background here again. I had a mistake. I didn't have enough parentheses to close off that original parenthesis that I opened up, so I'm adding one more here to go ahead and evaluate this expression. And now we should see that that input expression matches our expectation. And I had to refresh one more time. I think Wolfram Alpha is acting a little sluggish today. But we make sure that input matches what we are expecting. It takes that expression that we're subtracting from 1 in the denominator and puts it in the denominator of the denominator to make that exponent positive. But all that matches up, and we get 1,975 even. So the amount they'll have to pay per month is $1,975. Then we're asked in part B, how much will they pay before they own the house? So we take the original amount, $63,250, plus the $1,975 that they'll pay, $1,975 that they'll pay in 180 equal installments, to get a total of $418,750. And then in part C, we're asked how much they're paying in interest. To figure that out, we take the total amount that they pay, subtract out the original purchase price of the house to get $143,750. That is, in order to purchase this house that cost $275,000, they actually ended up paying over $418,000, and over $143,000 of that was just towards the interest on the loan. So that formula can be a little bit tricky. Just be careful with parentheses as you enter it in, and you can always check that input that Wolfram Alpha gives you to make sure that matches what you were expecting to have entered in.